Good evening, all of you. We were discussing diffraction at n slit. We have already discussed about single slit diffraction. For Fraunhofer single slit diffraction, the expression for intensity comes out to be a square sine square alpha by alpha square, where alpha is pi by lambda e sine theta. E is the slit width. In this particular case, the maxima is observed whenever alpha is equal to 0. This corresponds to central maxima, and the intensity is maximum in this case. A square limit alpha tending to 0 sine square alpha by alpha square function goes to 1, so the intensity is a square. Minima is observed with this function whenever alpha is equal to n pi for all values of integers n not equal to 0. Limit alpha tending to n pi, this a square sine square alpha by alpha square function goes to 0, so the intensity is minimum. The first minima will correspond to alpha equals to pi, and if I substitute the value of alpha, which is pi by lambda e sine theta equals to pi, I can evaluate the value of theta to be equal to sine inverse lambda by e. Continuing further, we see that the secondary maximas are seen whenever alpha is equal to n plus half pi for all values of n starting from 1 onwards. The intensity in that case becomes a square times sine square n plus half pi divided by n plus half pi square. Thus, we observe that the successive maximas show a decrement in the intensity in ratio. If I see the ratio goes somewhat like this. In the ratio, 1 is to 4 by 9 pi square, is to 4 by 25 pi square, is to 4 by 49 pi square, and so on, where each secondary maxima is seen consecutively at 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on. Now, continuing further, we want to discuss the case of a diffraction grating. A diffraction grating is a collection of large number of slits. So you have large number of slits, and in this case the slit width is considered as E, and the opacity, the region which blocks the flow of light or the passage of light, is known as the opacity, is of length D. And this E plus D is known as the grating element, which is nothing but width of one transparency and one opacity. Now we assume single slit diffraction is occurring at each of these slits S1 to Sn. Now these single slit diffraction patterns of n slit overlap together to form n slit diffraction pattern. From each single slit, the amplitude that is coming out is equal to a sine alpha by alpha, the same expression which we have seen for single slit. So the amplitude from S1 is a sine alpha by alpha. Similarly, the amplitude from S2 is also a sine alpha by alpha. But these two waves differ in phase by an amount which is equal to 2 pi by lambda times E plus D sine theta, and we are calling it specially as 2 beta. So whatever is coming from S1 and whatever is coming from S2, they are equal in terms of amplitude, but there is a phase difference between them, and that phase difference is 2 beta. Thus we see that each of these differ from the previous one by a successive phase difference of 2 beta. Thus we have n consecutive waves of amplitude r, which is a sine alpha by alpha, and they are having a consecutive phase difference of 2 beta. Thus, the final resultant due to n slits is given by r dash, which is equal to r times n sine beta by sine beta, where r is a sine alpha by alpha. This gives my r dash to be equal to a sine alpha by alpha sine n beta by sine beta. Thus, the intensity, which is square of r dash, is equal to a square sine square alpha by alpha square sine square n beta divided by sine square beta. This is the expression of intensity due to n slit. Now we have to find out the positions where it is going to be maxima and minima. So let's study this particular function. Since the intensity is a square sine square alpha by alpha square sine square n beta by sine square beta, we observe that alpha is a slowly varying function while beta is a rapidly varying function. If you go back to the expression of alpha and beta, we know alpha is pi by lambda times e sine theta while beta is pi by lambda times e plus d sine theta. Therefore, beta is rapidly varying and thus we have to focus on this particular function, that is sine square n beta divided by sine square beta, and see where this function maximizes and minimizes. Now for principal maxima, for all values of beta equals to n pi, what will happen is that if I put beta equals to n pi over here and here, this becomes a 0 by 0 function, and by applying L'Hospital's rule, its value comes out to be equal to n square. So for beta equals to n pi, we are going to get maximum. Special cases when alpha is also 0 and beta is 0. Initially, when beta is 0, alpha is also 0 because pi by lambda e sine theta is 0, pi by lambda e plus d sine theta is also 0. So now the intensity at that particular point where alpha and beta both are 0, this function in the limit alpha tending to 0 becomes 1, and this function in the limit beta tending to 0 becomes n square. So the intensity is maximum, which is equal to n square a square, and this is known as 0th order principal maxima. Moving on to next value of n, whenever beta is equal to n pi, we are going to get this function as maximizing itself to n square. So the intensity will be equal to n square a square sine square alpha by alpha square. Now this sine square alpha by alpha square function will slowly decrease from 1. So the value will be slightly less than the 0th order principal maxima, but yet it will be counted as a principal maxima. So the condition for principal maxima is whenever beta is equal to n pi, where n gives you the order of the principal maxima. Okay, let's moving ahead further. For minima, we need to check out where this function goes to 0. And since we are focusing on this particular function, what we realize is whenever sine square n beta goes to 0, but sine square beta does not go to 0, this function reduces to 0. So the condition is that sine square n beta should be equal to 0. That means n beta should be equal to an integral multiple of pi. But sine beta should not be equal to 0, which means beta should not be equal to an integral multiple of pi. And thus what we realize is, comparing the above two expressions, n should not be equal to m by n, or else this m should not be an integral multiple of n. Consider the relation. Let's take an example where d, the slit opacity, and e, the slit width, are related as d is equal to 2e. This will help us to estimate the value of alpha and beta related to each other. So now what we get is alpha is equal to pi by lambda times e sine theta, and substituting the value of d will give you beta to be equal to 3 times alpha. And to make it more clear, let us consider a limited number of slits. Normally this number of slits is very large, but right now we are taking number of slits equal to 5. So now we are going to plot the intensity on a graph by taking n equals to 5, beta equals to 3 alpha, and let's see how does the graph looks like to understand the positions of maxima and minima. So now what we have seen is that for alpha equals to 0, on this side, on the x-axis, we are plotting these three parameters, alpha, beta and n beta. This is the slowest varying function. Beta is the second most rapidly varying function, and n beta, as obvious, is the most rapidly varying function, which means that when the value of alpha goes to pi, the value of beta becomes 3 pi and the value of n beta becomes 15 pi. So now what happens is, the first condition, the principal maxima occurs at alpha beta going to 0, n beta is also automatically 0 at that position, and that is equal to n square a square. This particular maxima is known as the 0th order principal maxima because n was considered to be 0 here. Now, when we put n equals to 1, that means beta is equal to pi, right? Small n we are talking about. Alpha at that point is pi by 3, and this satisfies the condition of, again, principal maxima, the one which we have discussed over here. For beta equals to n pi, we are going to get a principal maxima. So the next principal maxima occurs over here for beta equals to pi, alpha is pi by 3, and n beta is 5 pi. Now n beta has changed from 0 to 5 pi, which means that in between n beta was pi, 2 pi, 3 pi, 4 pi, and so on. So therefore, we have to check out where this function minimizes and maximizes. As we have seen previously, for minima, n beta is an integral multiple of pi. So the moment n beta is equal to pi, we are going to get the minima. So over here, we see that the first minima occurs at n beta equals to pi. When n beta is pi, we are getting the first minima. Beta in that case is just pi by 5, and alpha is pi by 15. So the first minima occurs over here. Now immediately after the first minima, you are going to get these secondary maximas. These secondary maximas do occur when sine square n beta goes to 1, and sine square beta in that case is something different from 0. And this happens when n beta is n plus half pi, because a sine function will attain a value of 1 for pi by 2, 3 pi by 2, 5 pi by 2, and so on. So what we observe is that for n equals to 5, between the 0th order principal maxima and the first order principal maxima, we see 3 secondary maximas and 4 minimas over here. This becomes the second order principal maxima, and so on. Similarly, we should get a third order principal maxima over here, but over here what happens is suddenly alpha becomes pi, which is an interesting case. So what happens is that we get something called missing order. When we look at the expression for intensity, we observe that this sine square alpha by alpha square function is also decreasing as alpha changes to higher values. So when alpha goes to pi, beta goes to 3 pi, n beta goes to 15 pi, even though this part of the function is maximizing, the other part of the function goes to 0. So the overall intensity goes to 0, and the third order of the spectrum goes missing. This is known as missing order of the spectrum, and it occurs when alpha is some integral multiple of pi, and simultaneously beta is also an integral multiple of pi. So the condition for missing order is that for a given value of theta, when both alpha and beta are some integral multiple of pi, we are going to get a missing order. So alpha is an integral multiple p of pi, and beta is also n pi. When these two conditions are simultaneously satisfied, in that case, we represent the condition for missing order. So just have a look at the condition for missing order, and this condition is really important. We want to go back to the intensity curve to once again focus on what we are saying. So we get the 0th order principal maxima in this case. First order principal maxima comes. In between these are secondary maximas and minimas. We get the second order. This third order should be coming over here, but could not come because alpha goes to pi. Therefore, what we are left with is the next maxima, principal maxima, occurring at 4th. If we extend further, we'll get the 5th order principal maxima, and the 6th also goes missing. So this concept of missing order should be absolutely clear to you, and you keep getting numericals based on missing order. So please try and understand this whole concept. We'll continue the next lecture in the next class. Thank you.